There are two important allosteric inhibitors. And again, that's why I say you need to know what allosteric means, okay? That's why we spend that time on enzymes. I'm not going to go ahead and explain it each time. Two allosteric inhibitors, ATP and citrate. The way to think of them, to kind of remember, is ATP is an indicator of a high energy status in the cell. This is not good. Citrate is also an indicator of high energy status. So if the cell has energy in the cytoplasm, plenty of energy, it's probably not going to need glycolysis, because the purpose of glycolysis is to produce energy. So that's one way to remember how these work. So they're going to inhibit phosphofructokinase 1, PFK-1, and slow down glycolysis. Two important activators, AMP, allosteric, again, activators. And this new molecule, I want you to pay attention. It's called fructose 2,6-bisphosphate. It's distinct from this one. That's fructose 1,6-bisphosphate. Okay? Actually, this is probably the most important molecule for glycolysis, for PFK-1, to activate PFK-1. In fact, PFK-1 doesn't really work if you don't have some of that, a little bit of that. Typically, allosteric regulators, activators, or inhibitors, you don't need high amounts of them. You just need small amounts to bind to the enzyme and change its activity. So I'm going to skip this slide. I'll go back to it in a minute. But now I want to first focus on this molecule and tell you how it's made. Okay? So just to orient you, this is fructose 6-phosphate from the second step. PFK-1 is phosphofructokinase 1 is going to produce fructose 1,6-phosphate. So that's the third step of glycolysis. Glycolysis therefore continues down in the through that way, this way. I want you to pay attention to this molecule, which is a completely different molecule. It has a phosphate at the 2 position, and it's called fructose 2,6-bisphosphate. It has nothing to do, per se, with this linear glycolytic pathway, except that it is a very important allosteric activator of PFK-1, and that's what that plus means, allosteric activator of PFK-1. So I'm going to tell you now how it's made. It's made from fructose 6-phosphate by another enzyme called PFK2. And the 2 tells you you add the phosphate at the 2 position. So this is not a glycolytic enzyme. It's a side pathway. However, this enzyme is important in producing this important allosteric activator. That's how it's made. It so happens that after a meal, insulin rises. Insulin causes the covalent modification, or specifically the dephosphorylation of this enzyme. When you dephosphorylate this enzyme, you activate it, and then it can form fructose 2,6-bisphosphate. Okay? You form this in the cytoplasm, it's going to activate PFK-1, and that activates the rest of glycolysis. So I want you to appreciate this is a not directly involved, PFK2 is not directly involved in PFK1, but it's important in producing this allosteric activator of fructose 2,6 bisphosphate. Fructose 2,6 bisphosphate, allosteric activator of PFK1. Actually, while I'm here, I just want to say there's an enzyme that breaks this molecule, removes it. And it's called FBP2, or fructose bis-phosphate 2, phosphatase 2, and takes it back to here. So by removing it, it stops the activation of glycolysis. So now I'll tell you how the interplay works. And I'll go back here and try to confuse you as much as possible. Because it is kind of a busy slide. At first look, it's kind of challenging. Okay? So first of all, you know, sometimes the abbreviations and the nomenclature aren't always consistent in all textbooks. So I'm just going to say to you, we want to focus on this molecule, fructose 2,6 bisphosphate, because it activates the important glycolytic enzyme PFK1. How it's made and how it is removed. How it's made is by this single protein, really. You see this single protein? It has two enzyme activities. One of them is what we just talked about, PFK2, that makes fructose 2,6 bisphosphate. And the other one is FBP2, which breaks this molecule. Now, both of these, guys, I'm just going to remind you, you remember covalent modification, what it means. It's adding phosphate to the enzyme protein, serine, threonine residues. You can add phosphates to both by a specific protein kinase, and it changes the state of activity of both enzymes in opposite ways. So the phosphate really is added to both. So let me go with the state where we are going to produce a lot of fructose 2,6 bisphosphate. And that will be in the well-fed state when you have glucose in the bloodstream and insulin in the bloodstream. Okay? So insulin is going to, first it activates the receptor, but through a cascade of steps will end up causing the dephosphorylation of this protein that has both enzymes. Okay? By a phosphatase. And I want you to pay attention and see what happens here with the colors.
The green for PFK2 means that it is active, which means it can take fructose 6-phosphate and make fructose 2,6 bisphosphate.
So now you produce the activator that is needed to activate PFK1, and therefore you activate glycolysis. Also important to note, the other enzyme whose function is to break down this molecule, fructose 2,6 bisphosphate, is inactive under the same conditions when insulin is high and glucose is high. So it can't do anything. Okay? So you produce this molecule under well-fed conditions when insulin is high, when both enzymes are dephosphorylated. In the dephosphorylated form, PFK2 is active. It produces fructose 2,6 bisphosphate. The amount of this molecule in the cytoplasm increases, and then it can allosterically activate PFK1 and activate all of glycolysis. Okay? You with me? Kind of?
If you like this video, please subscribe. Thank you.